Hi everyone, and thank you for joining this fourth 2020 EoCoE webinar. So today's webinar will be an introduction to the FTI library, and it will be hosted by Keller from the Barcelona Supercomputing Center. So allow me to extend my thanks to Kai for being the host of this webinar, and I hope everyone will enjoy it. Kyle, I'll give you the floor.
Okay, thank you very much, Julian. Yeah, as he said, my name is Kai Keller. I'm a PhD at the Barcelona Supercomputing Center since September last year. But I have been working on FTI since about 3 years at the BSc as a software engineer. And today I'm going to show you the very basics of this library. So like a short introduction, what you can do and how you can do it with FTI. I hope you all are fine with regarding to the situation what we have right now. Okay, then let's get started. So this is the outline. First, I will give you a short motivation why we do need checkpointing. After that, I will show you a little bit the theoretical background. Then we go into the library, so what we can do with FTI. After that, I will show you how you can do this. And the last 2 points is the performance check evaluation with 2 examples on large scale and the outlook. Okay, so now the question is, why do we need checkpointing at all? Nowadays, on the clusters what we have today, I would assume, regarding my experience, that we have something which is called mean time between failures, MTBF, of about 12 to 24 hours. So when you have a application that runs on large scale on one of the current clusters, you would actually need some kind of resiliency measure in order to finalize your application successfully. And this becomes even more critical when you go to larger scale. So we have the exascale coming, proposed for, let's say, next year. And there we have expected mean time between failures of hours. So it's extremely important that it's crucial to have some fault tolerance measure in order to get the application to the end. And the most common one and the most general one that you can basically apply to, let's say, a very large set of applications is checkpoint and restart. However, the naive approach, so just saving the data, the checkpoints on the parallel file system, is not really scalable, because when you can imagine that when you have a petabyte of data, it takes hours to store that. So we need something more smart here, and there is where FTI comes. I will show you why later. So the idea is extremely simple. So the idea is just you protect your application by every now and then, so frequently saving the application state to storage, run, and when something happens, you do not have to fall back to the beginning. You just roll back the whole application to the last checkpoint. So you take the data, what you have stored to that checkpoint, you load it to the buffers, and you run. So, and it can, of course, it can happen several times, but this is the measure what we take. And the overhead is simply the time that it takes to store the data to the storage buffers. And this depends obviously on the time, on the size of the protected data. The more data you have to store apart, the longer it will take to store this data. And as well on the frequency. and the I/O bandwidth. So, and this bandwidth also depends on the storage layer that you use. So, the parallel file system, when you have a lot of data from many processes, will take longer than storing everything locally to the node, for example. When we look at the of the whole run, we can imagine that we have several failures during one run. So we have to take into account the time that it takes to recover from the checkpoint, plus the time that it takes to rerun the computations that we have to redo, which are from the last successful checkpoint until the failure. So this is the complete overhead what we have when we protect our application with checkpointing. However, if we would not do that, we would not be even able to finish at all. So this is something what we have to take into account. There are different kinds of checkpointing. Something which is for us right now not very interesting is the kernel level. That is rather for operating systems to roll back to a healthy state when something happens to the system. What we are interested about today is the user level checkpointing, and there are different kinds also. So there's something which is called transparent checkpointing. This is in most of the cases a library that you link to your application, and this library looks for the memory footprint in terms of mapping, so what is mapped from your application, and dumps all this to the stable storage. And so it just basically doesn't look at all what your application does. So it just takes the snapshot of the whole application and stores it to a file system. There are some libraries which give you a little bit more control about this. You can, for example, exclude certain regions from that. So you can have a little bit of control then. However, you have a lot of redundant data or data what you do not need. You save way too much, basically. The good thing is that you do not have to look in your application. You just link it and you're done. But when you want to have more control and when you want to introduce better performance in your application, you need to look into the application itself. So it needs some kind of API-based scheme, and that is the approach what we take in FTI. So FTI is API-based, written in C, so you can easily use it also in C++. Totally, we have done this several times. And we have an interface in Fortran, so you can also use it for Fortran applications. Then here is that what I mentioned before, naive approach, just storing on the parallel file system. We have 4 levels here. So not only that, we have 3 other levels that can store the data locally on the nodes. And I will explain all these levels in detail later on. So that is the term multi-level checkpoint library, is that you have you can apply a flexible checkpointing scheme. FTI also provides something which is called asynchronous post-processing. We call it simply head process. So it's one dedicated process per node that can take on a large share of the work you have to perform when you do the checkpoint. We support also hierarchical storage layers. So parallel file system, storage on the node, storage servers, and you can find the library on GitHub. And on that GitHub, we as well have the documentation and the manual. Recently, we have added read the docs, and we have Wiki. So for us, really, it's important that we have like a good documentation, so that you find easy access to the usage. Every API function is documented there. We have also one example for all of these functions, so that you can look up how you can properly use this function. There are videos and so on. So I really encourage you to go to this, read the docs, and to the wiki to eliminate any question what you have. You will find good information there. Okay, so multi-level checkpointing. What does it mean? It means, as I said already before, that we offer a flexible checkpointing scheme. So not the naive approach, just dumping everything on the parallel file system. We have also some more interesting approaches. And recently we added also an interface that uses the native API from DDN IME, so that we can also store to the parallel file system using the IME storage server. These levels, so these 4 levels, what we offer, they are characterized by the grade of the level of resiliency, overhead, and power consumption. And we can set the frequency manually, either in the configuration file or by hand in the application itself. So in order to offer these multi-level characteristics, we need to know something. So essentially what we need to know is where every of these processes run. So on which node do the processes run. In the beginning, on the initialization, FTI builds a list and assigns every process to a node, so that we know, okay, this process is here, that process is on another node, and we build some kind of clustering. So in the configuration file, you set a size for the group, and FTI groups all the nodes into these group size groups. I have a very nice graphic where I can show you that a little bit more intuitive. These groups are essential to achieve this clustering, but also they are important. The group size is important for one of our levels which works with Reed-Solomon encoding, because when the group size is too large, this encoding takes too long, and yeah, that I will show you later. Okay, so this is basically how FTI builds the topology. These gray rectangulars here are the nodes. These black rectangulars are the processes, and the blue rectangulars are the group. So you can see that processes on the same node never belong to the same group. That is very important for the certain levels. So that is what FTI does in the beginning. It assigns processes to the groups, so that we have processes grouped together which are definitely not laying on the same node. So okay, so what are these 4 levels, what I'm talking about? We have 4. Level 1 is the fastest one. Level 2 is a little bit slower, and level 3 even a little bit more slow, and level 4 the slowest. But they are also ordered according to their reliability. So level 1 is the fastest, but the less reliable. Level 2 is a little bit more reliable, but a little slower. What does level 1? It simply stores the data from each process locally to the nodes. This can be in memory when the node offer disk, for example, so DEV, SDV, yeah, and SSDs or NVMEs. So one of those local storage devices. So that is level 1. Simply as that. Level 2 is a little bit more sophisticated. It takes the data from each process and we store it first of all on the node, same as level 1. But then we take that and we copy this data to the partner node. So to the partner process, which is definitely on another node, as I showed you before, which is also known as buddy checkpointing or partner checkpointing. Then we have level 3. We use erasure codes there. In our case, it's Reed-Solomon coding. And this groups 4 processes, or like in our case, it will be 4, as I will show you later. But you can set the group size, so it groups the processes which belong to one group together and creates as many files as processes are in the group, redundant files. And we can lose half of the files and recreate the data from the remaining files. So that is the strength of this erasure coding. You lose half of the data, but you still are able to recreate the full set with the remaining ones. This is level 3. It takes some time to encode the data, so that it's why it's a little bit slower. And then we have level 4, finally, which does not store locally, but globally. So we store all the data at the parallel file system. This is, of course, the most reliable, but also the one with most of the overhead and the least scaling behavior. And now I will go in detail what the levels are doing. So very simple. Level 1 is placing one checkpoint file on the node, and this is, yeah, it can be really fast, especially when you use run lists. However, when you use only one of these files or one node, then this data is forever lost and you cannot restart anymore. So this is good when you have a soft error. These kind of errors you can always tolerate, but as soon as you have like a loss of some of the checkpoint files, then it's not possible to recover anymore. Level 2 is a bit better there. Since we have doubled the data, we can use theoretically half of it. So we could basically use half of the nodes and would be still able to recover. However, we cannot lose, so this would be the case where we can recover, but when we lose to consecutive nodes, then this would not be possible anymore. So it's significantly more reliable than level 1. And on a failure, we can simply recreate the whole checkpoint by loading either the checkpoint data from the partner node or recreating the redundant copy to the partner node. So that is level 2. And level 3, again, we store the checkpoint files locally on the node and create redundant files from all the group members and placing them on the node as well. And in this case, we achieve a significant increase of reliability, because even if we lose 2 consecutive nodes, we are still able to recover, because as this is one characteristic of Reed-Solomon encoding, that you can lose half of the group members, and it doesn't matter which. So as long as you have at least half of the group members left after the failure, you are able on the restart to recreate the whole checkpoint data and recover successfully from the checkpoint. And finally, level 4, storing all the data globally on the parallel file system. We have different modes on this level here. So we have the default mode, which just stores the data end to end and processes, produces N files. We have interfaces to MPI-IO and cyanlib, where we have one shared file for all processes. So we store N processes to one file. We have HDF5, which can store end-to-end and end-to-one. And the strength here is really that we created the HDF5 interface in such a way that you are able to produce the global data view. So when you imagine you have a decomposition of the application running, you will recreate this view of the data, the local data, so that you can create the contiguous and complete data set on one single HDF5 file on the parallel file system. That gives you the possibility to evaluate the data which you store in the checkpoint, which is commonly the data what you are interested in. You can visualize the data, you can post-process the data. You have like also some kind of time evaluation, because you will take not only one checkpoint, you can keep the checkpoints and so on. So this is a really nice feature what we have added recently. And also recently added is an interface to IME, to the DDN IME storage server, as level 4 checkpoint. That works like this, that you have this storage server, which operates like a buffer between the application and the parallel file system. And it handles the data much faster than the parallel file system itself. And so it makes it possible to write directly to the parallel file system, so to say, but using the IME storage server in between. Yes, and since the data is on the parallel file system, we can even, of course, we can tolerate the whole cluster outtake as long as the data on the parallel file system is fine. So this is the most reliable. Okay, so I mentioned, and when there are some questions, I think you have the possibility to raise hands. Otherwise, I think it would be good if you just remember until the end what the question is, and then we can dedicate some time maybe later on to answer some questions which are there. Okay, so I mentioned that we have a dedicated process in FTI that can take on some work from doing the checkpoints. We are calling this process internally heads in FTI, and we have one per node. And how this works is that it performs the post-processing work from the checkpoints locally to transform those local checkpoints into 2, 3, or level 4 checkpoints. And here is how it would look like to visualize this a little bit. We have 3 processes here. They arrive to the checkpoint, write the data locally, perform the post-processing of the data inline. And since we have a collective checkpoint here, coordinated checkpoint, we have to agree, all the application processes have to agree on the successfully completion of the file in order to continue the execution. So this is the case where we have no head processes. This is the case where we have a dedicated FTI process, so one head process per node. And we have the 3 processes again. They write the data locally to the nodes, and the FTI the head process post-process this checkpoint further and transforms it to the corresponding checkpoint file. So as an example here for level 2 and for level 3, we have seen that first we write the data locally, and when we have the dedicated head process, that is all what the application processes have to do. They dump local the data, and then the dedicated head process does the rest of the work asynchronous to the application processes. And that can be happening for level 2, 3, and level 4. So this gives an enormous boost of performance to the application. And we have also implemented this for HDF5, so that you can store, so that you can achieve having a global checkpoint file in the HDF5 format with the contiguous data sets, however performed only by your application processes locally to the node. And the post process merges all the single files afterwards to one shared file on the parallel file system. So that is what FTI can do, the basics. But now the question is how. And here is the introduction to the basic API. So we have with these 4 functions, you could essentially do all that what I have shown you before. We have FTI init and finalize. This is simply initialization, reading the settings from the configuration file, and finalizing, freeing buffers, and so on. So important function is FTI protect. This function exposes the buffers that you would like to include in the checkpoint file to FTI. And what you need to pass to this function is essentially an ID, the pointer, and the number of elements, and the type. So that gives FTI the possibility to know where the data is in memory and how long the data buffer. And we can then, at time of the checkpoint, include this data to the checkpoint file. So this is basically registering the data to write it into the checkpoint file. When the pointer changes or the size changes, there you need the ID, what you have signed to this buffer, in order to call the same function again and update the pointer or the size information. FTI snapshot is some kind of automatic checkpointing. It's placed, for example, in the main loop, and you specify in the checkpoint, in the configuration file, the interval of each of the checkpoint levels. So you give FTI knowledge about when you want to perform level 1, when you want to perform level 2, 3, or 4 checkpoints, and FTI snapshot measures the iteration time and decides, okay, now 1 hour is passed and we can now perform a coordinated checkpoint at that iteration together. This will be then according to the configuration file, either level 1, 2, 3, or 4. Then when we restart the application, this function as well checks whether it is a restart or not. If it is a restart, it initializes the buffers, what we have protected before, with the data from the checkpoint file. Okay, so this is basically in the simplest of the cases what you would do in order to protect your application. In order to have more control of, or when you want to really checkpoint on an iteration basis, you can also use the functions checkpoint, recover, and status. Checkpoint on call performs immediately a checkpoint of the desired level and ID. And this function status, maybe before, is a request of what do we have? Do we have a restart, or do we have a clean run? When we restart from a failure, this function returns 1, and we know, okay, we have experienced a failure and we have to recover the data before continuing. And then we call recover in order to load the data from the checkpoint file to the buffers and continue from the last checkpoint. If you use arrays of structures, for example, and not native for types, so every native type already is available to pass as an FTI type, the FTI protect function. But when you use structures, self-defined structures, you can define the type within FTI. You can create derived types using this function. Okay, so this is a simple example, a mini app, so to say, just to show how we can use it. This we initialize FTI passing the global application communicator and the path to the configuration file. After that, we protect our buffers. Here it's the rank and the iteration counter. We assign IDs to these buffers. We pass the number of elements and the FTI type of this buffer. And we enter the main loop. We place FTI snapshot here in order to perform checkpoints at the desired time or recover to the protected buffers on the restart, and finalize FTI in the end. And what I haven't mentioned before is that FTI also provides a communicator, which is also very important when we want to use the head case, so the asynchronous post-processing of the checkpoints. Then we have to use this communicator in the rest of the application, because FTI internally splits the global application communicator into an FTI communicator for the head processes and an application communicator for the application processes. So when you don't use this FTI convert here, you will definitely end up having deadlocks and these kind of things. So this is very important. Normally just assign to the global communicator variable in the beginning, for example, MPI com equal to FTI convert or something like this, and you use this communicator variable throughout the application. Sorry for the noise here. I hope you don't hear it too much. Okay, so the same thing we can also do using the other functions that I have shown you before. So instead of FTI snapshot, we can use recover and checkpoint here, and status. It's the same thing, but using checkpoint and recover. So we initialize, protect. On the restart, this will return 1. We recover the data. We enter the loop at I equal to that what have been stored in the checkpoint file, and we continue execution. And we take checkpoints corresponding to this variable here. And at the end, we finalize. This is an example of the configuration file. This one here is the glorious head variable. So we can employ FTI to do asynchronous post-processing of the checkpoint files by setting this to 1. When it's set to 0, then we do all the checkpoints inline. We specify the node size, the group size, the checkpoint IO, which would be the default HDF5, IME, CyanDip, MPI IO. These variables are set by FTI. This will be set to 1 when we have performed 1 successful checkpoint, so that if the application crashes, we can know that we have experienced a failure. If you want to test FTI on your local laptop, it's important to set local test equal to 1. Then we simulate the cluster underneath. So that way you can also use level 1, level 2, and 3, because they need to have like different nodes underneath. Otherwise, they will not work. Then important is that this checkpoint directory here is local on the nodes. This is the checkpoint directory for level 1, 2, and 3. This one here is for level 4, and it has to be on the parallel file system, accessible from every node, especially when we want to use MPI or SignLib. And the meta directory as well has to be on the global directory. Then just the last thing what I want to say from this configuration file is this one here. We have the intervals of the checkpoints. In that case, we have after 3, 6, 9, 12 minutes, perform level 1 checkpoint, 5, 10, 15, 20 minutes, level 2, and so on. When we have the case that 2 checkpoints supposed to be performed at the same time, level 1 and level 4 at minute 33, for example, FTI will take the more reliable checkpoint. So in that case, would be level 4. Okay, so far so good. Then let's see what it does in practice. How does it look? So this one is on the EoCoE supercomputer in France. It has local node storage SSDs, and we have used the dedicated head process in order to perform the checkpoints, and we have compared the whole thing to a normal level 4 checkpoint without head process. So what we can see here is that the behavior of all the checkpoint levels, so independent of the checkpoint level, we have like some kind of perfect scaling behavior, constant scaling behavior when we use the head process, because essentially what we do every time, independently of the level, we do a level 1 checkpoint when we use the head process. And transparent to the application asynchronous, this head process performs then the post-processing and transform this level 1 checkpoint to the corresponding level. And as comparison here, so these lines, green, yellow, orange, and purple, these are level 1, 2, 3, and 4 checkpoints with activated head. So we can see all they take more or less the same time. And the line in light blue is, as for comparison here, a level 4 checkpoint that is not taken in line. So that is not used the head process for. So we can see that we have more or less like linear scaling behavior here, and like significantly more overhead when we do not use this head process. Then another test was performed on Mira from Argonne National Lab on 32,000 processes, I think with RAM disk here, but it's not as that important, since it's just a comparison from head and non-head case as well. So we have an execution here, 3,000 seconds, so about 1 hour, and we have the execution here using the head process. So we save already here 10 minutes in, so we have here about 50 minutes, and here we have 40 minutes. So it's 10 minutes faster in this short application run. So it's quite an increase. Okay, so we have, here is a short summary. We have a flexible multi-checkpoint strategy. So we have different levels. We have level 1, 2, 3, and 4, which we can apply in however manner we want to. We have automatic checkpoint and recovery. We can use these strategies, so we can change the strategies. For instance, when we use FTI snapshot, sorry, by changing the configuration file. That means that we do not have to recompile when we want to change the configuration. Then I have presented the global HDL5 checkpoint files creation, and recently implemented, we have checkpointing from GPU buffers. And this works like this, that you do not have to specify that this buffers comes from the GPU. You simply pass the pointer from these buffers, and FTI will know that this comes from GPU or CPU. So you treat GPU, and it's kind of a heterogenic view which FTI offers there. From your side, you treat GPU buffers and CPU buffers just the same. In addition to that, what I have shown you before, we have, for example, also differential checkpointing, which is storing only the changes that have been made from towards the last checkpoint. So that can reduce the I/O work, and incremental checkpointing, which gives you the possibility to add the variables separately to the checkpoint file. So when you want to, you have several buffers protected in FTI. How it works is you initialize the incremental checkpoint mechanism, you add the variables whenever you want to, and you finalize the incremental checkpointing mechanism. This has some advantages. I don't want to go into detail here, but it is possible to using this to, for example, overlap computation and checkpointing work. So to make checkpointing, in the best case, even completely transparent. But I will not go into detail here. What we cannot do is we cannot completely we have no asynchronous checkpointing in that sense. So we have to do coordinated checkpoints. So we cannot checkpoint. We cannot, for example, continue the execution and only one process occurs failure and restarts and so on. So this is not possible right now. We have coordinated checkpoints here, so everybody has to restart. And we need the wisdom of the developer in order to apply this checkpointing. Yeah, I hope that you got everything more or less. If there are any questions, please let me know now by raising the hands. Okay. Yes, hello. Eric, you can talk.
Do you hear me?
Yes, I hear you.
Okay, thank you. Eric Boyer from CNS. I would like to know, are there any restriction for checkpointing? I'm thinking about IP sockets or sessions or communication between nodes.
Sorry, can you specify the question again? Here was some noise.
Okay. I was just, my question is about what are the restrictions that can apply on, that may apply on FTI process. I mean, an open socket for any kind of communication between nodes, are they handled by the checkpoint process? Or do we have in the application take care that these phases are not active?
Yeah. Okay. So when I understood you correctly, you say that there could be any interference between checkpointing and the normal application flow when you have internal server communication or something like this between the nodes. Is that right?
Absolutely right.
Okay. I would say that this cannot really occur because right now, since we have a coordinated checkpointing, the application completely stops when we perform the checkpoint. So we all the application processes agree on one time. They call the checkpointing function, which is a blocking function. We perform the checkpoint, and after that, we release from that function, and the application continues. So I don't think that there can happen any interference in that sense.
Okay, that means that the good practice means that you have the semantics of the implementation of your FTI directives in your code must take into account this fact. Okay.
Exactly. Yes.
Okay. So it's a good way for avoiding that, because it's always the thing is coming back when an outside process of checkpointing without any modification of the application occurs. The sockets and communication on the flight are not handled by external checkpoint.
Yes, that's right. Now that is the approach what FTI takes here. So it's good and bad. So it leaves all the responsibility for the correctness to the developer, because it's an API-based application. We do not something what you don't want. But as well, you have to put some effort in to reach this. Okay.
Okay. I have another question. If possible, to have two questions for one guy.
Of course, it's possible.
Okay. You didn't get very far on the way the FTI process is handled. You talk about a dedicated process or something else. Is it a thread, a spawn, or something like that to handle the activity?
Yeah, so it's let's assume you have you do not fully use all the processes on the node. Then you should use the head process. So it's really an MPI process. It's not spawned. It is part of MPI convert from the beginning, and on initialization of in FTI, so FTI init. Before FTI init, the global communicator is that what you pass. After FTI init, the global communicator is FTI convert, and the global communicator is split into two groups. So the head processes use their own process communicator, and the application process use the communicator, basically global communicator minus head process communicator. So it's not a thread and it's not spawned. It's part of the whole MPI process set from the beginning.
Okay.
Okay.
Sont activés. Sont coupés.
Just a second. I will mute. Okay. So I have here Jordan Denif, who has also a question. Yeah.
Hello.
Yes. Hello.
I'm Jordan Denif from Karlsruhe, and I have a following question. So I will start with a sub question. How does it perform with a job scheduler, or what shall I do in this job scheduler? Call my application, which is pre-compiled with FTI, or should I call the FTI that calls my application? Can you just describe the whole process? What should I do if I have an old Fortran code that is MPI parallelized and with domain decomposition? What should I do as roughly steps in order to get then the FTI working with my code?
Okay, so I actually have planned to do a small live example here, how to implement FTI into a very, very easy application. And I think that is relatively general. So what you have to do in your application is to decide where you do want a checkpoint and which level and in which frequency and so on and so forth. And once you have decided that and you have implemented it and it works, you should potentially also be able to use the head process just by enabling the feature in the configuration file. So the first step is implementing checkpointing with FTI in your application. Make sure that it works, that it checkpoints and restarts upon failure. And then you should also be able to use the head process out the box. Is this okay when we go into the live example? And after that, you can again ask me if you are satisfied or not.
Yeah, that's good. When shall we do this live example? Right now or next time?
Yes. So I think there are. Let me see if there's another question. I think there's a question. And I will answer that question, and then after that we will directly go to this live example.
Oh, thank you.
Okay.
Yeah.
Thank you very much. Was there another question from your side, Eric, or is this?
Yes, it is just to go in the same direction that the previous one. I think for a production on a big facility, scheduler integration is unavoidable. So sorry for making this waste of time. So if you have some samples of how integrate in Slurm or something else, please go ahead. Thank you.
Okay, yeah, this I'm not going to do the Slurm integration, but in general, it's not really needed to implement this into Slurm, because it's basically once you have integrated the API into your application, it's part of your application. So the behavior of the checkpointing will be part of the application flow. And there's no Slurm integration planned of FTI in that sense. But anyway, I will start now with this live example here, and it's still time for questions in general. Okay, so. Okay, so can you, I hope, please raise hands if you cannot see the terminal. Okay. So I cloned the repository before, and I will just show you how to build the whole library first of all. So. It's already a build folder. So in order to build the library, you create a build folder, and we use CMake. So you can use the basic command, just CMake, and you define an installation directory here, and press enter, and then we configure the build environment. And after we have done that, we install the library. And it's a relatively small library, so it should go relatively quickly to install this. So now it's installed, and we will build an example on that. So first of all, we need to export some environment variables. The first one is so that we can find the library without pointing to it when we compile the application. The second one is for the shared library usage. And the third one is in order to find the head file without passing it through the compiler. And so this is really from scratch. So it will be just really a very, very simple example. But it will also show the strength of FTI, or the what you can do with FTI basically. Okay, so first we have to include the headers, MPI and FTI. And then we create two buffers. This will be the size of the buffers. And then we initialized MPI. So MPI has to be initialized before we initialize FTI. Then we initialize FTI, and we are going to pass the path of the configuration file. And the global communicator. Afterwards, we protect the buffers. The first parameter is the ID. The second one is the pointer. Then the number of elements. And I just saw here that there we have to change to double. And this one here is the FTI type for integers. The same we do for the other one. And now we can already call FTI checkpoint. The first is the ID of the checkpoint, and the second is the level. And I'm gonna perform 4 checkpoints here. So the first checkpoint will be level 4. The second one will be level 3, 2, and 1. I'm doing this in order to show the behavior of FTI when we take different kind of checkpoints. The behavior is that FTI will keep the checkpoints of high reliability as long as the next of that level will be taken. So level 4 checkpoint and 3, and so this statement here will lead to having one level 4, one level 3, 2, and one level 1 checkpoint at the end, because when something happens for level 1 to the recovery, we can still fall back on the next reliability level in FTI. If we would take another level 4 checkpoint here, we would delete all the former checkpoints. And what I'm gonna do now is I finalize MPI. Without finalizing FTI, just to like simulate a failure. And let me just quickly look through. But I think it should be fine. Okay. And now I need a configuration file. And what I do here is I will take the configuration file from FTI, the default configuration file. This is the default configuration file, and it has a lot of comments here. So the default configuration file has all the explications, what everything stands for there. So to simplify the handling of the configuration file, we will go with head equal to 0 now, and I will leave everything as is in this checkpoint file. And let's just hope that everything works out. Okay, it compiles, that is already good. So right now we have nothing here in this folder. But when we now execute, we have seen, okay, we have performed a couple of checkpoints, and these checkpoints are stored here. So we have locally a level 1 checkpoint, a level 2 checkpoint, and we have a level 3 checkpoint. The way how this works right now is that we simulate nodes. So we have directories which simulate separate nodes here. I have to go. Okay. So in order to perform the restart, so these are the checkpoints here. Now we want to perform a restart. We request the status from FTI. So if it is a restart, this will be returning 1, and we are going to perform a recovery. So, and to make this whole thing a little bit more meaningful, I will assign values to the array elements. Something like this. This actually should paste this here. Okay, that looks better. Okay. So, and what I'm going to do here is to check if the values are indeed the correct ones. Okay, so this looks about right. Yep. Okay, let me see if it compiles. Okay. Ah, okay. I have also already a version for that if I really mess it up here. In the worst case, we can change to that. But that looks good. So, and now we have the config file here, failure equal to 1, which means that FTI supposedly would know that it is a restart, and we would be able to perform this restart here. And obviously I did something wrong here. Of course, I have to perform everything again, obviously. So we are going to set this equal to 0 here for marking it as a plain start. We run and we restart when we recover successfully from level 1. And what I want to do here as well is to finalize FTI when we have successfully recovered. Okay, so we have successfully recovered and we have finalized FTI. So what I want to do now is I run the application again. So we have 4 checkpoints here. So what happens if we lose the level 1 checkpoint, for example? So we delete all the level 1 checkpoints here. So we can see there's no level 1 checkpoint anymore. And formerly we have recovered from level 1. Successfully recovered from level 1 because that was the most recent checkpoint file here. And what we do is we can see here FTI does not find level 1 checkpoints. Recover failed from level 1, but we can still recover successfully from level 2 with checkpoint ID 3. Then what we can do is we can completely remove all the local checkpoint files and try it again, and we will see that all the local recovery fails, but we still can recover from level 4. Another thing what we can do is so if there are any questions, please don't hesitate to ask. But what we can do now is we can remove, let's say, we can remove two non-consecutive nodes here. So we have only node 1 and node 3 left. We lost 0 and 2. What potentially should happen is we cannot restart from level 1, but we can restart from level 2 because we have the partner copies from node 2 on node 3 and from node 0 on node 1. So what should be happening is that we restart from level 2, and that is what happened. Okay, and if we delete node 0 and node 1, we still can recover from level 3. So that is basically everything what I wanted to show from the live example. Is there anything what somebody of you would like to see or would like to ask else? So please raise the hands or mark questions. Is there anything from your side, Leo, if you are still on the call, what you would like to mention? Leo, can you hear me? Okay, that doesn't look so well.
Can you hear me, Kai?
Yeah, I can hear you. Yes.
Yeah, no, I was just saying that I think everything was covered more or less well. Yeah, one thing that just to precise concerning Eric's question about integration with Slurm is that there might be some ways to integrate a little bit better FTI and take some advantage of Slurm or other schedulers, and we are looking into different options. However, this is right now not part of the EoCoE project. But yeah, there are some things that could be done in order to improve this the recovery after a failure. With everything that Kai showed today, we could try to have a little bit more elastic recoveries or things like that if there is support from the scheduler. But other than that, I think it was everything very, very clear. Thank you, Kai.
Thank you very much. Okay, so if there is nothing else, I have nothing from my side.
Okay, then in this case, allow me to conclude this webinar by saying once again that I'd like to thank all the participants. And thank you, Kai, not only for the webinar, but for the real-time demonstration. That was very instructive. The next EoCoE webinar will take place on April 20 at 11 as well, and will be hosted by Herbert Owen, also from BSc. He will be discussing, making an introduction to wind resource assessment using CFD with examples. And I hope some of you will join us for this as well. And in any way, shape or form, there will be future EoCoE webinar coming this year as well. So take care, everyone. Be safe in these difficult times. And I hope you found this webinar interesting. Thank you, everyone. And guys, thanks to you, really.
Yeah, thank you very much. And have a good time from my side also. Goodbye.
Goodbye, everyone.